And I would like to invite to our virtual studio our next speaker. And if you saw his shorts on our YouTube channel, you know that he's also not alone. Adam, hello, welcome to Java on Conference 2023.
Hi there. I hope you can hear me and see me well.
Yes, yes, for sure.
Perfect. Hi, how are you tonight?
Very good, very good. So we had two great
Good to hear.
speakers, and now we have two more. So guys, stay with us, stay tuned. So how's Oscar?
Oscar is sleeping peacefully in a nice living room. Hopefully he won't be disturbed by my yelling about abstractions. If he is, I might need a little bit of a break to calm him down. Otherwise, everything is fine.
Okay, that's great. Mine Oscar is also sleeping in the room nearby, so I do hope he won't not disturb us. He's a bit bigger than yours, guys, than your dogs. So if he will disturb us, he will disturb us for sure. So yeah, we will dive right into Adam's talk right away. Before we will really do that, guys, I would like to remind you that we have two chats, one on the YouTube and another one on the Weir community platform, and we do expect your reactions, your comments there. So please share with us your opinion, share with us what you think about the conference, your questions, of course. And also, I would like to remind you that on our platform, we have ability to vote for talks and we have ability to give badges for our speakers. So this is how you may share with us your opinion right away. Of course, there will be feedback form after the conference, and we will appreciate if you will fill it out. But still, please do this right now because, as I mentioned several times, it's online, and in online it's really hard to really understand that you are there on the other side of the screen. So, and I know that you are there because I see numbers somewhere, but still, it's really good to receive some messages, some thanks, and etc., right in the middle of the talks. So, saying that, I would ask Adam to share his screen. So we will be able to show it. And yeah, two more talks left. Still some offline activities, online activities, I mean, there. Please make photos for Instagram, tag us there. And yeah, that's it what I wanted to share. Adam, good luck, and let's go.
All right, thanks a bunch. So first of all, before I get started, I would like everyone to get some sort of mobile device or maybe open a different tab on their computer and then scan this QR code or go to menti.com and use this code because we will have some interactions and well, this is the only way to have it other than the chat, but I don't trust the chat, so please. Ideally, you would be watching this on some screen and then you would have your phone nearby anytime some question pops up on Mentimeter, okay? So I will tap to the next one. And I'd like you to say something if you're in. Hi, hey, yeah, that's perfect. I will wait for a few more people, let's say 20 seconds. And then we can get started and I will switch back to the main thing. Friday, haven't heard that before. Grüezi. Okay, 36 and counting. Okay. All right, so back to the main thing. So this is Abstractions, the Good and the Bad. I'm Adam, hi again. And there is two reasons I created this talk. One of them is that I'm just fascinated with abstractions altogether and the way they enable us to create incredibly complex things without going crazy in the process. I think they are the main things that allow us to do that. And the other is that I am passionate about writing clean code. I think writing clean code is one of the nicest things developers can do for each other, and I'm all for that. To me, the best definition of clean code in the book itself is this one. Clean code never obscures the designer's intent, but rather is full of crisp abstractions. So this is not from Uncle Bob, this is from the preface by Grady Booch. And I love this because it's just one rule that contains all of the other rules, right? So if you really understand this one, you don't even have to think about the others. But to use this one, you must really understand what abstractions are. So this will be my first question to you, and we'll head back to Mentimeter. And let's establish a baseline. So please rate your overall understanding of abstraction. So if I say abstraction and you say abstro what, then you just say 1. And if you think I can ask you anything about abstractions and you'll be totally fine and you can explain it to me, then you should put 10. Okay, we have some pretty confident people here. The confident people answered first, and now the less confident people are mustering up the courage to chime in. That's great. So if it's already 10, you can, you might as well leave. I mean, I can't tell you anything new. But if we have an average of 6.7, yeah, I think we can improve a little bit. And some responses are still coming in. Yeah, 5 more seconds. Okay, so we have an average of 6.7. So basically, this audience is fairly comfortable with the concept of abstraction, but leaves some room for improvement, right? Which is great. Now, as the title implies, abstract can be a good word or a bad word. So if after this talk you go out and tell your friends that my talk was pretty abstract, then you probably don't mean it in a good way. But if you're using a new library with a very complicated API and you say, can't they just abstract all of that away? Then it sounds like you're a fan of abstract. Something can be just abstract enough or too abstract or not abstract enough or not abstracted the right way. So there's plenty of material for a talk with this title. It's a huge topic. I won't provide any comprehensive theory, but what I want to do is to first zoom out, get a wide view, so we have a common understanding of what abstraction really is in a general sense. And then we will go down a few rabbit holes, especially related to how the brain works, how that relates to the code you write, what those have to do with each other. And yeah, that's it. If you need a quick clarification anywhere, just post it in the chat, or if you're able to, then unmute yourself. Longer questions, let's discuss those at the end. So let's jump right in. Abstraction is all over the place. As developers, we create them every time we take something complex, give it a name, and hide what it exactly does. And this happens at all scales. So if you are defining some web service endpoints, decoupling the layers of your application, or extracting a method, we have abstractions everywhere. It's our primary tool for splitting a problem horizontally into individually manageable and reusable layers. But abstraction is not just our thing. By definition, and this is the best one I could come up with, there's many different definitions, I would say anything that isn't just one concrete thing, like this iPhone right here, right now, or this table right here, right now, is abstract. And an abstraction is just something that was made to be less concrete or more abstract than it was before. So based on that, if you're a carpenter, you don't create abstractions that often. But if you do any sort of knowledge work, like we all do, then almost everything you create is an abstraction. But who else does it? The abstract of a medical or scientific article is a one-paragraph summary of its contents. So the basic findings are pulled out of the article and presented there. And this way, you can learn about the findings without reading all the details of how they came to those findings. Abstract art is art that's just not concerned with accurately representing things from the real world. Maybe it's a simplified form of reality with some detail removed, or it's completely detached from reality. This way, there's no meaningless elements to catch the viewer's attention, and they have a better chance of appreciating the artist's real intent. In language, every word is an abstraction. It holds much more meaning than just its letters, but usually not more meaning than what you need at the time. So because you have the abstract concept of a chair, you can say, "May I get a chair?" instead of going crazy, looking everywhere for something to sit on and saying, "Please, can I?" Maps abstract away real-world terrain, only showing some characteristics that are important for planning your journey, so you can find where your connection is before you miss it. Now, in some of these fields, abstraction is fractal or at least composite in nature. So you can dig into an abstraction in search of the concrete implementation, but actually you just find some other abstractions that you can also dig into. So the inside of one abstraction is very often just the outside of another. This is most true in language. There, every word in a sentence is an abstraction that can be looked up in a dictionary and evaluated into a list of other words, which are also abstractions that can be looked up in a dictionary, and so on and so forth. You can keep flipping the dictionary round and round and never leave the realm of abstraction. Luckily, you can combine these abstractions to make up magical phrases that, when uttered, open a window to reality, like "my left shoulder." Software, well, it's similar, but not quite the same. You can debug all day through your code, clicking into all the standard library methods, getting lower and lower, until you eventually find some machine code that you can't click into anymore. So that's concrete now? Well, not really. It's still an abstraction, but you've hit the limit of your debugging environment. But when you execute that code and get some voltage moving in the circuits, well, that's not very abstract anymore, I would say. Interestingly, in art, abstraction is just not composite at all. So imagine some abstract art, for example, some face without any details of the skin, just a few lines. The details are not there at all. If you want to see details, you have to imagine them, and that will be different for every person. So it's just completely different than other fields. So people in all of these fields know very well that they create things called abstractions, and it means something different to each. But there's one thing in common to all of them. All abstraction involves hiding detail for which we don't have the time, the space, the interest, or the brain capacity. And to me, brain capacity, like maybe you saw in the promo, is the most interesting, because if you look at the others, well, you can spend more time, usually. You can get more space if you get creative. You can pretend to be interested, but good luck trying to get more brain capacity, right? So let's pick that as the next rabbit hole we're going down on. First, a disclaimer. For the next several minutes, you will not hear anything that seems even remotely related to computer science. Instead, I'll babble about mostly cognitive psychology and the likes. And, I'm not a psychologist. But if you bear with me, eventually you will understand why I'm doing this, and I think it will all make sense. So, brain capacity. This has been studied intensively since the 50s. And by now, there is wide consensus that in order to learn or understand something new, its parts have to fit into your working memory, which is like the RAM inside your brain. The problem is the working memory can only hold about 4 things at any given time. This does vary a bit between people, so it decreases with aging, alcohol abuse, chronic stress, anxiety, depression. Maybe don't do those things. It can potentially be increased with aerobic exercise and maybe certain memory games like N-back. But practically on any given day is a fixed number you're working with. So we will do a quick experiment here. Please log into Mentimeter if you haven't done so yet. And what we will do, you can let me know if you need the QR code again. I need to switch screens to go there. We will play a game. And the rule is this. I'll show you a number for 5 seconds, and you have to remember it. Okay? So, ready, set, go. And that's it. So get your Mentimeters and tell me, do you remember the number? There's always 2 people who remember. Okay. No way, no way, no way. So almost everybody has responded no way. I'll wait 3 more seconds. Okay. Now, we'll do the same thing once again. Rule is the same. I'll show you a number for 5 seconds, and you have to remember it. And well, I have to say, this is a bit more fair when I'm doing this live because it's a bit location dependent. So this might be easier for people who are in Switzerland. You will see why. But even for the others, I think it might be okay. So try to remember the number. Ready, set, go. All right. So same question as before. Do you remember the number? Round 2. Okay, you're all prepared. Everybody remembers? It's almost unbelievable. If you don't remember, please, you should also respond. Okay, so if we compare the first one, which was 4 people remembering and 30 not remembering, and then the next one, which is 32 people remembering and 1 person not remembering. Well, what was the difference? What happened? If you have an idea, just throw it into the chat. I'm interested. But what I think is that the first number, well, that consisted of 10 completely separate digits that had just nothing to do with each other. And the only way to remember them would be to cram each of them individually into your working memory. And, well, you just saw before how large the working memory is. So no way it won't fit. However, with the second number, what did you see? Okay, I'm looking at the chat.
So let me
Patterns.
pronounce these comments so they will not be
Yeah,
silent.
please.
So we have comments that we have abstraction in case of second number. Number was easy. Just need to remember 4 digits. Patterns, rules, groups. Yeah, also about patterns. Taxi number. Okay. Complexity halved with repeating numbers. And yeah, that is easily separated on groups. I think these are the answers.
Yeah, and some
Excellent.
people are also revealed that numbers look like phone numbers. I'm
Yeah.
surprised no one mentioned regular expressions. It's a Java conference.
So you would argue that the regex for this one would be smaller than the regex for the other one?
D+/D+, and that's it.
Okay, I'm not sure that's how the brain works, unfortunately, but yeah. So if you're in Switzerland, please also put that word into the chat. You know which word I mean. I'll wait for just 5 seconds for that. Somebody said Grüezi at the start, so I know there are people in Switzerland in the chat. But maybe too shy or not at the keyboard anymore. That's okay. So the second number, well, I think what some of you saw, maybe not exactly like this, but Swisscom, 4 times 4, 3 times 3. So this is a Swiss phone number. It's a made-up Swiss phone number, which is 079. That is the Swisscom provider. And then the rest of it, it's 4 times 4 and 3 times 3. So the thing is, your brains, however you did it, even though you're not in Switzerland, you recognized 3 groups. And fitting 3 things into working memory is not a problem, even if each of them contains more things. So you can remember 10 things by remembering 3. How is that possible? Well, all this is thanks to a built-in compression algorithm of the brain called chunking. Chunking is a fundamental learning mechanism that uses the power of abstraction. It enables you to learn things that are larger than 4 bits. Without this, you couldn't. And it's something that you have by the time you're just a few months old. Now, this is how it works. If you're doing it in a sort of a controlled fashion. You start by looking at a few small things that you already understand in your working memory. And you figure out their relationships and organize them into a group. Then you give that group a name or some sort of reference. It can be a sound, an image, a smell. And then you move the whole thing over to your long-term memory, which is basically a bottomless pit with huge capacity. And at this point, you have a chunk, one thing that contains some other things. And the cool thing is you can just think of the reference, but still have an intuitive understanding of the whole chunk without thinking of its details. So now the whole thing takes up only 1 slot in your working memory. And then you can form other similar chunks and combine them to form larger chunks. And this pattern is something you can continue practically indefinitely. So in theory, there's no limit, if you're doing this, to the complexity of the things you can understand. Now, I'm curious, is this process something that feels familiar to you, this chunking that I'm describing? So please go to Mentimeter and tell me, is the chunking process familiar to you? Not really, or, well, you've done it before probably, but you don't exactly know that it was chunking, or yeah, you're totally familiar with it and you know the concept of it. Okay, 10 more seconds. Okay. So we have 6 people who have learned about the theory of learning, 15 people who have learned before in a way that they were quite aware of how they learn, and 2 people who, well, so far didn't notice what they do. It's probably impossible that they've never done chunking, but they didn't notice that they've done it. Okay. So, like I said, what I've described is the controlled way of doing it. Very often your brain does this in the background in a more organic and messy way, but still sometimes you can do it exactly like this. And now I will show you an example. So let's say that you just bought your first ukulele and you want to learn Somewhere Over the Rainbow. Like you, I'm sure you know that song. It's legendary. I will just quickly see whether I need to tune here. Okay. One person is unable to respond in Menti. Please let me know if others have that problem as well, and we can look into it. Okay, so you want to learn Somewhere Over the Rainbow, but you have no idea what you're doing. You just bought this, literally. So first, you should learn to make a sound, right? And the first sound we will learn is called pluck, which looks like this. And to do that, when you don't yet know how to do that, you need to concentrate on 3 things. Placement, which part of your finger you put there and where you put it. Angle. And force. So you concentrate on 3 things and practice that for a few minutes, or depending on talent, hours or days. And after a while, you can just think pluck and do it. Pluck and do it. So placement, angle, and force became pluck. And now we have 3 empty slots in the working memory, so we should use them. We have 3 other sounds to learn, each of them consisting of 3 things. Now, we'll just imagine those 3 things that they consist of, but we have the first sound, which is the pluck. We also have the strum down, the strum up, and the slap. Okay, so we've learned those. Now, if we think about all of those, we are thinking of 4 things. So what do we need to do next to learn this, to learn more? Because our working memory is already full. Well, we need to create a group. So first, we will take strum down and strum up and just do both of them alternating. Then we will add a pluck on the 1 and a slap on the 3. Okay, now we are paying attention to 3 things again, and we have combined them into 1. What should we call this one? Well, it is the rhythm. Again, we've combined the strumming and the plucking and the slap into 1 thing, which is now the rhythm. Somebody can come over and say, remind me, what was the rhythm of Somewhere Over the Rainbow? And you can do, that one. And you can still think of 3 other things or talk about them, which also uses brain capacity, because the rhythm itself, well, it's now just one thing. You've practiced it, you've chunked it, okay? You could also do something else while you're doing this. So where are we? At this point, our right hand is pretty busy, but the left is not yet doing anything. So what we will do is learn some chords. That's the job of the left hand. Now, to learn chords, well, the easiest way to do it, if you're not that much into music theory, is to just memorize where each finger goes on the fretboard right here. So for the first chord, we can just memorize this one finger here. Then for the second one, oh, sorry, I need to do something. Something broke. Okay. Still not okay. But that's all right. I'll work around it. So for the first chord, we've memorized this one finger right here. For the second one, we will memorize this 3 fingers here. For the third chord, this one, and these 2. So we can learn all of these as a group. First chord, second, third, fourth. But now we have 4 again, so what do we need to do? We have to create a group. No need for anything fancy, just remember the first 4 groups. When you're learning music, you will encounter the powers of 2 lots of times. So just chunking something into a group of 4 is perfectly okay. Then for the next group of 4 chords, we can reuse some of the old ones and just learn 2 new chords. So this is one of the new chords. And one more. But we will reuse 2 others. So that's the correct one. And we will add one more group, which is just this loner, because it's 9 in total. So we have 3 groups of chords. Our working memory is almost full. We are panicking. How the hell can I learn this song? What do I do now? But we already know. We need to create a group. Now we have the chord progression. And when we're here, we can look at the rhythm again and recognize that, oh, we have 2 things. Why not combine them? So the right hand will do the rhythm, and the left hand can join with the chords. And now we have the whole song. I don't have more screen space for the graph, but at this point, this whole thing is just one chunk. So at the start of the song, there's also some humming by Is. It goes something like this. Etc. So once I've learned that as a separate thing, I can just put that and the chord progression and the rhythm together. And then I will have this. So even without the melody, based on my counting, I just learned something that consists of 41 things. How did I fit that into my brain? Well, it's thanks to chunking. I could do it because I did this in a way that at any one time, I did not have to pay attention to more than 4 things at the same time. So that is the power of chunking. Okay. If we look at what we have now on the screen, it's a tree-like structure with a lot of nodes. Cognitive psychology calls these nodes chunks. Chunking, chunks. But what else can we also call these chunks? I'm looking for a word here. Please put it into Mentimeter and let's create a word cloud. So these 41 things in the song I've learned, they are chunks. What else could they also be called? Okay, 5 responses so far. All of them are correct. There's one of them that's the most correct, but all of them are correct so far. Ten more seconds. Okay, so let's see what we have. Abstraction is in the middle, and yeah, that's what I was thinking of. And we will see why. Roadmap, that's interesting. Leaf, well, some of them are leaves. Patterns, yes, all of them. Partitions, yeah. Memoization, yeah, that's sort of a tricky process that you can do. Yeah, atomic parts, path, encapsulation, lots of good ideas. To me, the best answer is abstraction, and luckily that's in the middle. So each chunk here in the song was created by taking something complex, giving it a name like pluck or rhythm or song, and hiding its detail. So each node is an abstraction. So a chunk is just an abstraction that's created automatically in your brain, and your whole learning process is based on abstraction. From here on, I'll kind of use these words interchangeably: abstraction, chunk, thing. Please bear with me. So let's generalize a little bit. This here is a song I know, but in a more general sense, we can call it internal knowledge. Why did I say internal? Why not just knowledge? Well, it's different from external knowledge, like an application. Finally. Because I would say that an application is just knowledge about how to do something that's written down and executable by a machine. It can look like here, just like internal knowledge. Here, there are both layered hierarchies of reusable abstractions that reference each other. You can see this one, the code one here, as a call graph. So this could be your main entry point, and then below your methods are calling each other. Here we have the left hand and the right hand. Maybe here we have two modules of the two separate modules of the same application. This is collecting some data, and then this is processing that data and creating some reports. For layers, here we had the song. Oh, what's happening here? Sorry. So here for layers, we had the song, the rhythm, the sounds, the muscle control. Here, maybe we have application main, service layer, data access layer, then utilities and various adapters, right? So the internal knowledge here on the left, of course, that can also be your knowledge about an application. So in this model that I'm proposing, when you're reading and trying to understand code, you're basically moving the stuff on the right over here to the left. Sounds pretty easy, right? Well, these structures can look virtually the same, but often they don't. But I will argue that they almost always should. I will argue that if the stuff on the right already looks like something that could be on the left, then it will be easy to understand. In other words, if we structure external knowledge like code, like internal knowledge, it will be easy to understand. I think when you're looking at some clean code for the first time and you feel like it's just beautiful and you get it, it is because you could move it from the right to the left without having to fiddle with it. And on the other hand, when you've been staring at the screen for 2 hours trying to understand some code, and you even got the rubber duck out, but you're still pulling out your hair trying to understand what's going on, it's because in order to move it from the right to the left, you'd need either some sort of miracle transformation in the middle or brain surgery. Now, the only reason the structure on the left is so good is that it was created by your mind for your mind. So it fits your mind, obviously. It's not perfect. It has problems too. It's a lot of effort to create. If you don't use it, you will forget it. You can mix things up and it can be terrible to debug, but it fits your mind. Now, on the other hand, well, with external knowledge, there's no such guarantee. Let's look a little bit closely into what this really means. Internal versus external knowledge. The process of creating internal knowledge involves no translation. Basically, these chunks in your brain are code compiled by the machine that is going to run it. So when that is created, there's nothing lost in translation. The resulting structure is well chunked. What do I mean by that? So like you saw before, the details of each abstraction came from working memory of the person who's creating the chunk. So they can be recalled as is and will fit back into working memory. You could also say that the branching factor of this structure, which I like to call the chunking factor, is less than or equal the size of the working memory. Now, the structure is also well connected, because to learn something, you must connect it to something you already know. That's what happens when children keep asking why. They need to get to the point where finally they can connect what you're saying to some chunk that they already have, at which point there is a continuous chain of reasoning between the chunks. Plus, the included content is personalized, because to learn something, you must connect it to something that you already know, not somebody else. Maybe you're trying to explain machine learning to a chef. And first you start by saying, well, it's like, you know, if your dog, we have a lot of dogs here, so that's fine. If a dog behaves well, then you give him a treat. And if he doesn't, then you don't. But the chef never had a dog, never knew somebody who had a dog. Pretty sad life to have, I guess. So it doesn't mean anything for him. But if you say, well, a reward function is like when you have a recipe and you cook something. and then you taste it. If you like it, you leave the recipe as it is. But if you don't, then you change the recipe. It will click instantly because the guy is a chef. So this will make sense to you, internal knowledge. Now, this one we won't talk about that much today. But anyway, these are the properties I've noticed that result from the lack of a translation step. There might be others. If something obvious comes to your mind, please put it in the chat. I'm curious. Anyway, it follows that if we want external knowledge like code to match internal knowledge and therefore make as much sense as possible, sparing our brain capacity, then we should replicate these properties as much as possible. So how can we do that? We'll begin with no translation. When you create external knowledge, well, it always starts as internal knowledge. Like someone has a thought and writes it down as text, which is translation. Then somebody else comes and reads that text and translates it again back into thoughts. Today, we'll mostly be concentrating on writing in a way that makes reading as easy as possible. To skip this translation, we would need to download and upload our thoughts directly. Right now, we cannot do that. But good translation may be almost as good as no translation. So, to learn about good translation, we will look at some bad translation. What without why? John is working on some code, this one, and this is his mental model of the code. Pretty similar, makes sense, right? Now, John wants to do something, and so he has some problem on his mind. John comes up with a solution for that problem. John writes down the solution, but not the problem. So he writes down the what, but not the why. The result is John comes back a few months later and has no idea what he's looking at. Or somebody else reads John's code today and has no idea what they're looking at because the chunks do not connect. So a layer of abstraction goes missing. And there, our bad translation has broken our structure and we no longer have a continuous chain of reasoning. Let's look at a simple example to see how this happens. John's team is working on some new Scrabble game, and he is now implementing the logic to calculate the total points for the round. I hope you're familiar with Scrabble on a basic level. Now, John already has a function that counts points horizontally by checking words from left to right. So he starts by using that. But words are also valid vertically, so he wants to add that. He thinks the best is to reuse this function, but to rotate the board before passing it in. So he looks up how to rotate matrix counterclockwise and does it. So what happened here? John's mental narrative was something like, I need to calculate the total, so I need to take the horizontal, then the vertical, and sum those up. 4 things, right? And then he got into the weeds of how to do that and ended up writing something down. When Jane comes and reads what John wrote, what will her narrative be? I think it's something like look at the code right now. We need to calculate the total, so we need to take the horizontal, then take the horizontal again, but zip and slice and expand the what? Sure, eventually Jane will Google this and understand that we're passing in a rotated matrix, and that basically does a vertical check, but it will take her a minute to realize this. And there you could say, it's a minute. And you would be right, but it's a minute each for everybody reading the code every time they read the code. On the other hand, extracting a function like this also takes about a minute, and you only do it once. Then you can also do this. And if you have this, what is the reader's mental narrative now? It's the same as the writer's. I need to calculate the total, so I need to take the horizontal and the vertical and sum those up. And let's just now think about that minute that we mentioned. We'll go to Mentimeter again. What is the time complexity of this abstraction process if the abstraction is not written down? Like John just did. And then his colleagues will come along and create those abstractions in their minds when they read John's code. Let's see how much of you are into time complexity. Wow, some pretty substantial answers. N squared, 2 to the power of n factorial even. Okay. Well, 10 more seconds. Okay, that's a very even spread. Maybe we need to talk on time complexity then. Well, so in my opinion, based on my calculations, O of n is the right answer. So thanks for those. Because every time the code is being read, an abstraction is being created. If you think I'm wrong, do put it in the chat and tell me why. Now, what is the time complexity of the abstraction process if the abstraction is written down? Please tell me. Okay. Yeah. So I agree with O of 1. The person writes down the abstraction, and everybody who's reading it is just reading it. There's no creation anymore. So which one is better? O of 1, obviously. Sometimes we make these optimizations when we are writing code. Very often it doesn't make that much of a difference. If the code is not calling an external service, maybe we save 1 second per 1 million calls. But reading and creating the abstraction in the mind takes a couple of seconds or minutes or hours. So if we optimize this one, we definitely save a bunch of money for the company. In any case, I think abstractions lost in translation may be a primary reason for Kernighan's law. Debugging is twice as hard as writing the code in the first place. So if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. So what can we do about this? The solution is very simple. Notice that John was implementing the rotation. When he was doing that, his mental narrative included all the right words that should be written down. Now, if you think in English and code in English, then just write down what you're thinking, the way you're thinking it, and you won't have abstractions gone missing. And here, I'm actually curious, are you doing this? What language do you think in when you're writing code? Please tell me, because this is the easiest if you're thinking in English and then coding in English. You're thinking in good language. Okay. That's pretty abstract. Russian, okay. English. Let's see. Somebody is able to think in a programming language. Well, multiple people are able to think in programming languages. That's amazing. I can actually believe that. But anyway, English seems to be winning. So for now, let's leave it at that. And people who are not thinking in English when they're coding, yeah, I think their job is substantially more difficult. Okay, now, if this principle here looks a bit too simple, it's because it is. It solves the problem if you're working alone, but if you're in a team, you need something more. Sarah is an exceptionally clever girl who studied at MIT, runs marathons and plays memory games for fun, so she has a working memory that can hold 7 things. As she codes, she writes down all the abstractions in her head beautifully. So everything is fine for Sarah. But when her average colleague tries to read a method she wrote, by the time they are finished, they will have forgotten where they started. So by doing exactly what we said you're supposed to do, she has broken the structure for others in a different way. So there are too many chunks in the chunk. Our chunking factor is now larger than the size of the average working memory, and we no longer have a well-chunked structure. It means there's now too much detail to fit into the working memory. The reader is overwhelmed and cannot see the forest for the trees. And they need to do some mental gymnastics, create the missing abstraction in their head every time they read the code. In the end, this is also a missing abstraction, but the difference is the abstraction was never there in Sarah's mind because she never needed it. Now, I won't bore you with an example here. All of you have seen methods that just do too many things, and you can't process them all at once. Now, to avoid clutter, we need to limit the chunking factor. Based on what we've learned, if this is more than 4, we should probably hide more things. So we could have a simple rule like the 4 things rule of abstractions. Abstractions should not contain more than 4 things. But can you say how many things this is? Let's go to Mentimeter and please tell me. Seconds. I put 66 because, I put 66 at the maximum because there's the number of characters, right? Okay, let's go back here. Without a graph, it's much more difficult. In the literature, a chunk is the largest meaningful unit in the presented material the person recognizes. But for different people, this largest meaningful unit is different. If you're just learning to code, it might be 7 things: the type, the variable name, assignment operator, object, method, parameter, end of statement. It's already too much. But with some experience, maybe we get the foo from the DAO based on ID. Now, as your experience grows, your chunks become larger and larger. And that's it. I don't think we can count chunks. Something that might come close is the cognitive complexity metric offered by some tools. This will provide a precise number, but I don't like it that much because it tells you, hey, your method is 53. Do something about that. It makes me uneasy. What does it really mean? I'd like to propose something else, which to me is more fun. Previously, we said you should write down what you're thinking. Let's refine that a bit. Every level of the abstraction hierarchy should be fully expressible as one simple sentence we can tell our average colleague over a cup of coffee and have it understood and repeated back to us. The words of that sentence should actually be written down and emphasized. If all of that checks out, you have hidden enough things and no counting was needed. If by the end of the sentence you've forgotten where you started, didn't fit your working memory, if your colleague couldn't repeat it back, it didn't fit their working memory. Filtering happens automatically. Now, if your colleagues are not talking to you, the colleague can be a rubber duck, or something that I'm sure many of you are talking to nowadays, AI. Actually, this week I did what everybody else was doing this week, and I created a custom GPT in order to help me with rubber duck design. But I have to say, so far, I'm not very impressed with the results. For example, here I've inputted the code that we've discussed before, and 3 out of 4 times it told me that this abstraction is perfect, and it mentions horizontal and vertical, even though it doesn't. If you're interested in this, post it in the chat. I will share the link. You can play with it. But so far, I don't think it's good enough to use. Even though we might use AI for this now, I like to call this process rubber duck design, because the rubber duck encapsulates the idea that just saying something out loud will create some sort of magic that helps you get a clearer understanding of what's in your head. So we use rubber duck debugging to help us read code and rubber duck design to help us write code. Now, I think I still need like 5 minutes to finish. Is that okay? Do we need to rush?
We need to rush.
All right. In that case, I'm going to skip a few things here. There was another translation issue that could happen here, which is basically over abstraction, which is not enough chunks in a chunk, which is the opposite of what we've discussed so far, but it results in the same thing, an overloaded working memory. So, skip a few things here. And let's summarize. Abstractions are all over the place. Many disciplines use them for many reasons, one of them, and the most interesting, being to spare our brain capacity. Our active understanding is limited by the size of our working memory. We get around this limitation by using a process called chunking, which creates abstractions in the brain automatically. When we write code, these abstractions in our brains are translated to abstractions in our text editor. This can go wrong in many ways, resulting in missing abstractions, under abstraction, over abstraction, or the wrong abstraction. The fix is very simple, but very often it doesn't happen. You just have to listen to the abstractions in your head, say them out loud, discuss them, write them down. Now, at this point, I would like to ask, and I promise just 20 seconds, after this, please rate your overall understanding of abstraction like you did at the start. Okay, I like that. And we even had to skip one section. So that's nice. I think that's like a 2-point improvement overall. Very nice. Now, if you remember only one thing from the whole talk, please remember that the power of abstraction is built right into your brain. You just need to take what it gives you whenever it gives it to you. So thanks a lot. And if you feel like you would like a summary of this whole thing, you can scan this QR code and download the PDF. And that's it. Thanks a lot for your attention.
Great. Thanks a lot, Adam. Thanks a lot for your talk. I'm a bit sorry that we had to skip some sections, but still, thank you very much for such a great thing on our conference. So it's not first time. I'll be honest, it's not first time I hear this talk, but it's just still awesome. So thank you very much.
Glad to hear that. Very welcome.
Okay, so thank you very much. Thanks for being on the conference, and have a great evening.
Thanks a bunch. You too. Enjoy.